SafeCap project aims at developing modeling techniques and tools for improving railway capacity while ensuring that safety standards are maintained. This video demonstrates the tool support for the SafeCap project, which is called the SafeCap Platform. The platform allows engineers to construct and reason about railway schemas. It provides a schema editor, a project explorer, and a number of views for editing properties of various schema elements such as railway segments, junctions, train tables, etc. The tool is based on Eclipse and uses EMF, GMF, and Epsilon frameworks. The remaining part of the demonstration covers such topics as schema construction, safety verification, capacity assessment, and capacity improvement. In this part we will show how to construct a simple flyout schema. We start with creating a new SafeCap project and a SafeCap diagram. We construct the schema topology using nodes and segments. Segments represent railway tracks, while nodes represent their boundaries. Every segment has two nodes on its ends and is characterized by its length, measured in meters. For a given topology, the tool produces schema elements such as routes, lines, and embeds. It also automatically generates signals and speed limits to protect junctions. Schema elements, such as speed limits, signals, and platforms, can be added manually as required. The boundary nodes of a schema represent points where trains would leave and join the given schema during simulation. These are represented by sink and source nodes accordingly. Having defined a schema, we proceed with its safety verification. The tool verifies the topology of the schema, control tables, signal and speed limits positioning. Let us start with opening the control table of this schema and deliberately removing some of the embeds associated with the route. Now we'll try to verify this schema and the control table. Both of the tools fail to verify the schema. One of the tools is a model checker. It reports a counterexample that we can use to analyze what steps in the model led to the safety failure. We can now fix the problem and try to verify it once more. The tools used are essentially scripts written in a simple object-oriented language provided by the Epsilon framework. This particular script connects to the Pro-B model checker. It uses an additional EGL script to translate the railway model into the B formal language. The tools are user-defined and are stored in the Eclipse verification project. Let us define a custom tool that checks that all the routes of the model are less than 400 meters long. The new tool now appears under the verification dialog and successfully executes. If we require the maximum length of a route to be 1 kilometer, then the tool fails and it returns a report. In this way, a user can define his own tools, and the verification process is customizable. In this part, we show the capacity assessment tools. We start with the blocking time matrix. This is a capacity estimate computed by a formula. It takes into the consideration schema topology and control tables and gives a figure that may be used for relative comparison between similar schemas. Similar to verification scripts, we can also define custom capacity assessment scripts that should be located in the capacity project. They can be executed over routes or lines, and the assessment results are shown under the capacity report. However, the capacity assessment presented so far is only a quick estimation. For a more precise assessment, the platform provides a simulator. To use it, we need to define a simulation scenario. First, we need to define a set of train types, their names and physical characteristics. Then, we define a particular scenario for simulation, which includes information about when and where trains appear on a schema. The result of the simulator is a graph showing distances as functions of time for every train. The simulator also returns a heat map, which represents usage statistics for every mbit per unit of time. Some mbits, typically junctions, are hotter than others because they are shared between different lines and have lower speed limits. To overcome this bottleneck, we need to modify the topology. The first thing to do is to create a genus of the original schema. The genus retains the same physical topology while removing all logical structuring. We will check the hypothesis that capacity of this schema may be improved by logical structuring with a regular block size. For this, we will write an automatic transformation pattern using the epsilon wizard language. The pattern traverses all the segments of a schema and splits each one into two parts, preserving the overall length. Let us now apply this pattern twice. As demonstrated by a simulation, the capacity of the schema is slightly better than that of the original schema.